In this video, I would like to explore these four sequences. We are asked to write out the first 5 terms for each sequence, and then to determine which converge and which diverge. And of course, we're going to support whether we think they converge or diverge with some amount of work, with some reason. So let's just get started writing out the first 5 terms here in number 1. I can probably tell what's going to happen if I take a limit as n approaches infinity on this first example without doing anything. But I've been asked to write out the first 5 terms, so I'm going to do that. So when I plug in a 1, I get 1 minus 1, and I get a 0 out. I go to plug in a 2, and I get 2 minus 1/2, that's 1.5, which I'm going to write as a 3 over 2. And then I just keep doing this. I'm going to plug in a 3, and I have 3 minus 1/3. And at this point, I realize that I actually think this one's easier to deal with if I find a common denominator and rewrite the nth term formula as an n squared minus 1 over n, because now on top I have 8, 9 minus 1, and on the bottom I have 3. And it lets me have an easier time writing out the sequence, realizing the top is always 1 away from a perfect square, and the bottom is just where we are in the sequence. It's the index of the sequence. So 1, 2, 3, got the fourth thing. That's going to be 15 over 4. And then finally 24 over 5. And that sequence would continue in that fashion. Well, at this point, as we go out in the sequence, those numbers do look like they're always rising. And if I take a limit as n approaches infinity of either n squared minus 1 over n or the original formula, I'll see that this is going towards infinity. Here I have a polynomial on top and a polynomial on bottom. The degree of the top is more, which means I'm running off to infinity. If I use the original nth term formula, I'd have n minus 1 over n. As n runs off to infinity, that goes to 0, meaning that this is equal to the limit of n as n approaches infinity, which is also running off to infinity. So not only does this diverge, we can write that it diverges to infinity. All right, here in the second example, I'm calling this sequence b sub n. I have 2 to the n minus 1 all over 3 to the n. Again, my first job, based on these instructions, is to write out the first 5 terms. Well, let's see, if I plug a 1 in on top, I'd have 2 minus 1 is 1 over 3. Plug in a 2, I'll end up with a 3 over 9, which typically probably write that as 1/3. My third term, I'm going to have a 7 over 27. 1, 2, 3, 4 on top. Let's see, 15 over 81. And then finally, one more term, I need to plug in a 5. That's going to be a 31 over 243. And that sequence continues on in that fashion. All right, well, looking at those terms, you might have a guess at this point about what's going on. I have a 1/3, 1/3, and then I appear to have numbers that are decreasing, though it's not always possible to tell what's going on in the sequence just by looking at the first 5 terms. So we need to take a limit as n approaches infinity. There are 2 different ways to evaluate this limit. One's easier, one is harder. I'm going to show you the easy way first. If I do the division here, I'd have 2/3 all raised to the n, because I have 2 to the n over 3 to the n, rewrite it like that, minus 1/3 to the n. Well, if I take the limit of just this part as n runs off to infinity, the bottom of that fraction is getting larger and larger and larger, and it's going to 0, giving me 2/3 to the n, which I know also goes to 0, because the base is less than 1. If I multiply 2/3 by itself more and more times, it gets smaller and smaller and smaller on the way to 0. So this sequence b sub n converges to 0. I did say there was another way to take that limit, and so just very quickly, sometimes students will think back to their Calc 1 and say, well, on top I have an exponential, on the bottom I have an exponential. As n goes to infinity, that's an infinity over infinity, and L'Hopital's rule would apply. So if I take the derivative of the top and the derivative of the bottom, I get here. Natural log of 2 and the natural log of 3 are constants, so I could pull those out front of the limit, leaving me with that 2/3 to the n. As n goes to infinity, that goes to 0. 0 times the number is 0. And there's another way of evaluating that limit. All right, number 3, I really liked this example when I found it. So let's write out its first 5 terms. What I like about this one is when I plug a 1 in, I get a -1 plus 1 is 0, and it doesn't even matter what that is, I get out a 0. And the realization is, if n is odd, I'll get a 0 there. So the odd spots in this sequence are really easy. 1, 2, 3, 4, 5 things. The odd spots are always going to be zeros. Now I just need to evaluate the even things, right? And so if I'm only writing out the first 5 terms, that's just 2 and 4, the second spot and the fourth spot. So if I plug in a 2, right, I'm going to get a 2 in this part, right, because it'll be a 1 plus 1 is 2, and here I'll get a 3 over 2. So 2 plus 3 over 2. Excuse me, 2 times 3 over 2 is 3. I don't know what I was thinking there, but I get a 3 out because I get a 2 times 3 over 2. All right, and if I plug in a 4, let's see, well, this bit would be 2 again, right? Again, a 1 plus 1 is 2. And in the parentheses, I would have, plugging in a 4, 5/4. So here I just get a 5 over 2. Not a whole lot of information here to figure out what's going on. 0, 3, 0 if I have 0, a number, 0, a number, 0, a number. And right there, I think I see what's going on. Because if I just looked at the odd values of n, the odd indices, this sequence is just a whole bunch of zeros. Right? If I just ignored the even things and wrote out the sequence of the odd terms, I would just get 0, 0, 0, 0. Let's see what we can think about if we look at the even indices. Well, whenever I plug an even number, that number out front, so I'm going to call this E sub k, the even sequence, right? The sequence if I just looked at the even terms. The formula would always be a 2, right? I have a 1 plus 1 is 2, and then I'd plug in an even number, add 1 to it, divide by the same even number, and so the way I'm thinking about that is a 2k plus 1 on top divided by a 2k, right? Because an even number is always a multiple of 2, and I can in fact simplify that formula to be 2k plus 1 all over k. And I can write out those first few things. I know I get a 3 and then a 5 over 2, and this formula would give me that 2. If I plug in a 1, I get a 3 over 1. If I plug in a 2, I get a 5 over 2. And let's just plug in the next few to find the next few even terms in the big sequence. And so a 3 would give me a 7 over 3. A 4 would give me a 9 over 4. And a 5 would give me an 11 over 5. And I think I see what's going on, especially if I imagine taking the limit of this. The limit, as k approaches infinity, of 2k plus 1 over k is 2. The even terms are converging to 2. The odd terms, definitely converging to 0. They all are actually, in fact, 0. So what's happening here is it's like I have 2 sequences in play. In the odd spots, I have a bunch of stuff that is 0. In the even spots, I have a bunch of stuff converging to 2. This limit does not exist. And when I say this limit, I mean the limit as n approaches infinity of the c sub n's. This limit does not exist. Because in the even spots, it's 0. In the odd spots, it's trying to converge to 2. It's like it's oscillating between 0 and numbers getting closer and closer to 2. This limit, this sequence diverges. That shouldn't get a dot, dot, dot. That should get an exclamation mark. Leave me with just one sequence to explore in this video. The sequence is recursive. I have a first term that's 1, and after that, the next term is always 2 times the last term minus 3. I have a little bit of a typo here in the formula, so I'm just going to rewrite it. So that's an a sub n plus 1 equals 2a sub n minus 3. Otherwise, it's self-recursive, and that wouldn't work. So this is the formula I need to be using. Let's just move on to another board and explore this sequence. So the first term was 1, and every next term is always 2 times the last term minus 3. Let's write out this first 5 values of this sequence. So this sequence appears to be called a sub n. The first term is 1. Plug that into the formula here, and I get 2 minus 3 is minus 1. And now I just keep repeating that pattern recursively. Plug in a minus 1, I get out a minus 5. A minus 13, 1, 2, 3, 4, one more to go. Let's see, that would be minus 26 minus 3 is minus 29. And while you can't always figure out what's going on in a sequence from its first 5 terms, I can tell what's going on in this one. Because after I have this negative number, I can realize every subsequent value is going to have to be negative, because I'm going to have a negative times a positive minus a value. This is a strictly decreasing sequence, and it's diverging to minus infinity.